Space is a curious place, and the sun is perhaps its most enigmatic aspect. The majority of the energy used by life on Earth comes from this source. This hot, luminous ball of hydrogen and helium sits at the center of the solar system. The diameter of 1,392,000 kilometers, the sun is 109 times wider than Earth. The sun is a yellow dwarf star that is 4.5 billion years old. It is the only star in our solar system located about 150 million kilometers from Earth. On our home planet, life as we know it would not be possible without the energy of the sun. The sun may appear to be a constant source of heat and light from Earth's perspective. However, the sun is a dynamic star that changes constantly and radiates energy into space. The sun's core is the hottest place in the solar system, with temperatures exceeding 27 million degrees Fahrenheit. The photosphere, the region of the sun we refer to as its surface, is only 10,000 degrees Fahrenheit. The corona, the sun's outer atmosphere, gets hotter the further it extends from the surface, which is one of the sun's greatest mysteries. The corona is enormously hotter than the photosphere, reaching temperatures up to 3.5 million degrees Fahrenheit. Recently, something massive has been observed around the sun. Although we can't glimpse the sun directly with the naked eye, and inching closer to the sun is impossible and sounds fictional, for the first time, NASA entered the solar system and is nearing the sun every day. In this video, we'll tell you about Parker's solar probe and its brilliant discoveries. A spacecraft has made history's first ever solar contact. Now that it's flown through the sun's upper atmosphere, or corona, NASA's Parker Solar Probe has taken samples of the magnetic fields and particle concentrations there. With this new accomplishment, solar science has been significantly advanced by the Parker Solar Probe. Touching the material that makes up the sun will help scientists learn crucial details about our nearest star and its impact on the solar system, just as landing on the moon enabled scientists to comprehend how it was formed. Parker Solar Probe touching the sun is a monumental moment for solar science and a truly remarkable feat, says the Associate Administrator for the Science Mission Directorate at NASA headquarters in Washington, Thomas Zurbuchen. Not only does this milestone provide us with deeper insights into our sun's evolution and its impacts on our solar system, but everything we learn about our own star also teaches us more about stars in the rest of the universe. Parker is making new discoveries as it circles closer to the solar surface, including from inside the solar wind, the flow of solar-generated particles that can impact us here on Earth. Parker found in 2019 that there are a lot of magnetic switchbacks or zigzag structures in the solar wind close to the sun, though it was still unclear how and where they originated. Since then, its distance to the sun has decreased by half, and the Parker Solar Probe has now gotten close enough to pinpoint its point of origin, the solar surface. Data on phenomena that are impossible to study from a distance will continue to be provided by the first flyby through the corona and the promise of additional flybys in the future. The Parker Project scientist Noor Rawafi at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland says, "Flying so close to the sun, Parker Solar Probe now senses conditions in the magnetically dominated layer of the solar atmosphere, the corona, that we never could before. We see evidence of being in the corona in magnetic field data, solar wind data, and visually in images. We can actually see the spacecraft flying through coronal structures that can be observed during a total solar eclipse." Parker Solar Probe was launched in 2018 with the goal of learning more about the sun by getting as close to it as possible. Parker has finally arrived 3 years after its launch and more than 20 years after its original conception. The sun doesn't have a solid surface as Earth does. However, it does have a superheated atmosphere composed of solar material that is magnetically and gravitationally bound to the sun. That material is pushed away from the sun by increasing heat and pressure until it reaches a point where magnetic and gravitational fields are insufficient to hold it in place. The Alfvén critical surface is the boundary where the solar atmosphere ends and the solar wind starts. The solar wind, which is created by solar material with enough energy to cross that boundary, carries the magnetic field of the sun with it as it travels through the solar system to Earth and beyond. The crucial point is that past the Alfvén critical surface, the solar wind travels at such a speed that its waves can never reconnect with the sun. When the Parker Solar Probe reached the precise magnetic and particle conditions at 18.8 solar radii, about 8.1 million miles above the solar surface on April 28, 2021, during its 8th flyby of the Sun, it signaled to scientists that it had finally crossed the Alfvén critical surface and entered the solar atmosphere. We were fully expecting that sooner or later we would encounter the corona for at least a short duration of time, but it is very exciting that we've already reached it. Parker Solar Probe repeatedly entered and exited the corona during the flyby, and this has demonstrated what some had hypothesized, that the Alfvén critical surface is not a smooth ball. Instead, its surface is wrinkled by spikes and valleys. Scientists can learn how events on the Sun affect the atmosphere and solar wind by figuring out where these protrusions coincide with solar activity coming from the surface. The Parker Solar Probe once passed through a pseudo-streamer, a coronal feature, as it dipped to just below 15 solar radii, roughly 6.5 million miles from the Sun's surface. Pseudo-streamers are enormous objects visible from Earth during solar eclipses that rise above the Sun's surface. The pseudo-streamer was similar to flying into a storm's eye as you pass through it, in stark contrast to the hectic barrage of particles that spacecraft typically encounters in the solar wind. Conditions inside the pseudo-streamer quieted down, particles slowed down, and the number of switchbacks decreased. For the first time, the spacecraft was now in a region where the magnetic fields were strong enough to control particle motion. These circumstances showed unmistakable evidence that the spacecraft had passed the Alfvén critical surface and entered the solar atmosphere, where magnetic fields influence all local activity. The mission has several corona passages planned, the first of which only lasted a few hours. Parker will continue to spiral closer to the Sun, eventually coming within 3.83 million miles, 8.86 solar radii of the surface. The Parker Solar Probe was scheduled for another flyby in January 2022, likely sending it back through the corona. I'm excited to see what Parker finds as it repeatedly passes through the corona in the years to come, says Nicola Fox, Division Director of the Heliophysics Division at NASA headquarters. The opportunity for new discoveries is boundless. Solar activity is another factor that influences the corona's size. The outer edge of the corona will grow as the Sun's 11-year activity cycle or solar cycle picks up, increasing the likelihood that the Parker Solar Probe will spend more time inside the corona. Unprecedented physics started to emerge even before the first trips through the corona. On recent solar encounters, Parker Solar Probe collected data identifying the origin of zigzag-shaped formations in the solar wind termed switchbacks. The data indicated that the photosphere, or observable surface of the Sun, is one location where switchbacks begin. The solar wind has turned into an unrelenting headwind of particles and magnetic fields by the time it travels 93 million miles to Earth. The solar wind, however, is patterned and structured as it leaves the Sun. A few strange S-shaped kinks in the magnetic field lines of the solar wind were found by the NASA European Space Agency mission Ulysses in the mid-1990s as it flew over the Sun's poles. These kinks caused charged particles to travel away from the Sun in a zigzag pattern. For many years, scientists believed that these sporadic switchbacks only occurred in the polar regions of the Sun. But at a distance of 34 solar radii from the Sun in 2019, Parker found that the switchbacks were not unusual but rather frequent in the solar wind. This sparked fresh inquiries and a resurgence of interest in the features. From where did they arrive? Were they formed on the Sun's surface, or were they the result of a process that bent magnetic fields in the Sun's atmosphere? One origin point is finally confirmed to be close to the solar surface by the new findings, which are currently under review by the Astrophysical Journal. The hints appeared as Parker orbited the Sun in its 6th flyby at a distance of less than 25 solar radii. Data revealed that switchbacks occur in patches and contain more helium than other elements known to originate from the photosphere. The scientists discovered the patches aligned with magnetic funnels that emerge from the photosphere between convection cells. These structures are known as supergranules, which help them further narrow the switchback's origins. The researchers hypothesized that the magnetic funnels could be the source of one component of the solar wind, in addition to being the origin of switchbacks. There are two types of the solar wind, fast and slow, and some of the fast solar wind particles may originate in the funnels. The structure of the regions with the switchbacks matches up with a small magnetic funnel structure at the base of the corona, said Stuart Bale, professor at the University of California, Berkeley, and lead author on the new switchbacks paper. This is what we expect from some theories, and this pinpoints a source for the solar wind itself. Understanding where and how the components of the fast solar wind emerge and if they're linked to switchbacks could help scientists answer a long-standing solar mystery: how the corona is heated to millions of degrees, far hotter than the solar surface below. While the new findings locate where switchbacks are made, the scientists can't yet confirm how they're formed. One theory suggests they might be created by waves of plasma that roll through the region like ocean surf. Another contends they're made by an explosive process known as magnetic reconnection, which is thought to occur at the boundaries where the magnetic funnels come together.